So what I'm doing right now is what almost every textbook, every GIS professor, every LiDAR handbook tells you. I'm creating a DSM by using the first returns. I actually think that's wrong. That gives you a DSM that's nice to look at, and if looking at it is your objective, okay. But I have one student that I'm supervising. Her name is Anahita Khosravipur. She studies at ITC Enschede, and she's about to finish, maybe in 6 months or so, her PhD. And we did a lot of work on making nicer height models, canopy height models and digital surface models. And there's two algorithms we developed. One is called the pit-free CHM algorithm, or the pit-free algorithm. And then we also created the spike-free algorithm, which improves a little bit on that. And let me give you an idea why it is a bad idea to use the first returns. I go to rapidlasso.com and I search for spike free. Okay. So, I mean, you can see that image on your own screen if you go to the blog. What can happen if you have first returns? What you see here is a tree, or two trees, or three trees, being scanned by, it's an illustration, being scanned by 4 flights. That are, the plane is always where those beams converge. And what you see here is also the scan angle. You know, those beams come at an angle, plus minus 30 degrees, 25 degrees, that's usually the angle. So what you see here immediately is the laser is looking under the tree. That means it creates first returns under the canopy of the tree, but also, this one here, on top of the tree. This one here is on top of the tree too, and then this one over there, it looks under the tree all the way to here. Now if you interpolate all the points that you see on this picture that are numbered 1, those are the first returns. If you make an interpolation through them, do I have a picture for that? I bet I do. Then it's going to look like this. It's full of spikes, and it's systematically, I mean, if you, because these are scanned on different levels, they have very similar x-y coordinates, but very different z coordinates, because you were looking under the tree. The same happens at houses, by the way. If you have a house, then if you look from this side, all you see is the roof of the house. But maybe the roof has an overhang. And now you scan from here, and now you can look under the overhang, and you get one here, and then one here. So it goes, and it creates spikes. And what do you do then? Well, this is my tin. Remember, it's a tin. This is just a 2D example of a tin. But the tin just looks just like that, except it's 3D. And then you sample it every 50 centimeters. Well, sometimes you hit the spike at the top, and sometimes you hit the spike at the bottom, and sometimes somewhere in between. It's very not good, the result. So, and also, I mentioned before, sometimes when you hit a cloud, like here, people cut off the first returns. Or like we remove the noise. That means the first hit is really the second hit. The second hit is now the highest one. But if you only use the first returns, you don't use these, and also on the lower canopy, you didn't use those. Those were second returns. So I think interpolating all the first returns doesn't give you the best. Actually, it gives you systematically a really bad DSM, which is okay for looking at it, because the spikiness of vegetation is actually useful to detect vegetation when you look at the hill-shaded version. But if you want to make a model to compute on it, I think it's not good. This is what I think it should look like. Like, if I could interpolate the points I really want to interpolate, I want to interpolate the points that follow sort of the top of the canopy. The digital surface model, that's how it's kind of defined in a way. It's the top layer. But that's not what interpolating the first return is. The first return is a zigzag thing. But everybody's using that. So we were thinking, how can we automatically create this one? And that's the spike-free algorithm, which here you can see some hill-shaded results of the spikiness. And I mentioned it before, especially along the edges of the houses where you have an eave, a roof that overhangs. It's like this. And you see that clearly in the hillshade. And look at the trees. I mean, it's a spike fest. And this is what the spike-free algorithm achieves. It gets very clean roof edges. And also the trees look less spiky. Let's look at some other examples. So quite different. And here's some screenshots from that make it. So that's really how the tin looks like. That's a tin that we will then raster. And it'll be fine on the middle of the roof and in the open street, but along the edges it just depends. You know, if you hit the top of the spike, oh, lucky you, you get a nice elevation value. But if you happen to go all the way down because your XY coordinate just happens to be right where the spike is, then you get something not so nice. And our tin is a spike-free tin. It looks like that, very clean edges, and therefore we are getting very nice rasters. It's very drastic. And here's the close-up on all those spikes along the house edges. And we don't have those spikes. And here's another. You see a walkway here, a walkway that connects the house with where the car area is. It's a covered walkway. Well, if you have a very steep angle, then the lasers look under the walkway, and so you have first returns on top of the walkway and under the walkway, and then you get that. And this is a very drastic example. And this is how spike-free looks like. I mean, look at the ledge here. It becomes very clean. You actually see that there is a ledge all of a sudden. The algorithm is, however, much more complicated. But it's implemented in LAStools. I don't really want to run it on the entire data set because it takes a while.